Okay, so it's great to have Maxime giving the last talk. It will be about augmentation, variety, augmentations for not VGA, from exact and non-exact fillings, from a Witten potential, and augmentation variety.
Something like this? Yeah, so there's this really great quote from a book review by Robert Langlands. It says this is a shallow book about deep matters about which the author knows next to nothing. So I think this is although, compared to the physics talks, I think we are on much sturdier ground. Anyway, so let's, with that in lead, let's begin. So, right, so recall from Hangao's talk, and by the way, my calculus students always say they can't read my handwriting. So if you also can't read, you should also speak up. Yeah, that is also true, but I complain to you. Anyway, so A, this is our Legendrian VGA, and we are immediately in the setting of the knots, and then, G star is 3, all that. So it's an algebra over Z H2 T star is 3 lambda K, right, which is to say Z Q plus minus 1 lambda I plus minus 1, sorry, plus minus, just, yeah, and then U I plus minus. I'm trying to keep the same notation as from this morning. I don't know if succeed. Right, so I'm immediately in the case of links. So there's more than one, there is a meridian and a longitude for each component. And the coordinates were introduced. Xi is log of lambda and corresponding pi. There's T and Q is T. All right. So then our augmentation variety, I don't know, our K, or actually, yeah, it's V of K. V of K is just the closure of, I'm not going to write it, so it's a closure of the top dimensional piece or component of the set mu lambda and q 0. This is now in C star to the 2n plus 1, such that exists an augmentation. Sending the corresponding coordinates to these numbers. So these are vectors of numbers, and epsilon of j is 0 sub j, and so on. Okay, so just this is mostly to recall the notation and not for any other significant purpose. So maybe a remark that in all computed examples, so in examples, for a fixed Q, the Vk is some kind of Lagrangian. So in the C star, where omega is sum over I lambda I mu I d lambda 1 over d mu I. And since I'm extremely explicit, of course, d lambda I is exi dxi, and so d mu I is dpi. So then we plug this in, and we get that this is also equal to some xp. Okay, so that's the standard form, and then hopefully once we get to here, this is another indication of why this should be true, at least on that branch. Okay. Right. Okay. So not only is it like that, so okay, preview, right? We're going towards this thing that appeared already in the previous talk, and then not only is it Lagrangian, it's also graphical over the x, zero, the zero section of our vector space. Okay. So this is part one of the review. Then part two of the review is augmentations. From exact feelings, and this has appeared in Roma's talk as part of kind of more general factoriality statement. So if I have WL, a exact cobordism from V plus to V minus lambda minus, okay. Right. Then I want to say that this induces some kind of morphism from A plus to A minus, a chain map between them. Of course, there is a little issue about coefficients. So with C coefficients as opposed to with homology coefficients, that's fine. Otherwise, I have to kind of use the inclusion of the ends to the cobordism and work with maybe coefficients of H1. Sorry, Z or C, H1, WL, maybe something like this. But okay, so for us it's simplified. So we are going to take the filling so that lambda minus is empty. So lambda minus is empty. And V minus. Okay, and we are still assuming kind of, I guess for this factoriality statement we need some, I don't know. In our case, certainly we have no closed read orbits, so everything works fine and so on. And so then we can define epsilon sub L from, A plus to and this is where I'm using the H2WL coefficients. By counting the rigid disks. So how is it defined, right? So first of all, for coefficients, as I said, we have if I have some kind of X or P or whatever it is, class, let's call it, I don't know. I didn't give it a name. C, no. In a H2 of V plus, lambda plus. Then I just send it over to I star. So epsilon L sends it to I star of C in this corresponding group. Okay. So for chords, of course, if it's not degree 0, then it goes to 0. So chords with degree 0. We look at the following. So EL of A is the sum over tau u tau of A e to the tau. Okay. Right. So what is this thing? Of course, well, this is some kind of count of disks. So what are these disks? So I have this A, the chord. I have capping for it. And I have a disk. So U over disk, one positive puncture going to A, and boundary on L, and then I can use the boundary together with the capping path to say that tau is the class of the boundary of U together with the cap. Oh, sorry. I guess I am doing the class in the relative H2, so I should just say U together with the capping disk or something. And so I sum over all these disks, their contributions in this way. So mu tau of A is just the number of these disks representing the class tau. Okay. Questions so far? Kind of introductory. Okay, so I wanted to review this and actually, look a little bit into the proof, because the proof would be exactly the thing that will get modified.
Proof of what?
Sorry?
Proof of what?
Oh yeah, I haven't stated that this gives an augmentation. So, okay, let's write the theorem. Epsilon L defined this way. So I know what to do on the coefficients, and I know to do what on curves. So is a chain map that is right. EL composed with these. Okay. Now we have a statement. We can look at its proof. Yeah, and of course, so maybe I should make a remark. That the way I think about this is that, of course, if I have a map to here, then I can kind of compose it with any assignment of the numbers to the variables corresponding to the homology classes, and I'll get an augmentation into C. This is kind of trivial. Any assignment. This will come up later, I think. Okay, so then we want to say that this is a chain map. All right, how does the proof go? Well, the usual way. So proof, maybe sketch or something. So consider MB, which is the union over all rep chords of grading 1, and of course over all tau in H2 of tau B. So this is the dimension of this moduli space is the grading of B, so is equal to 1. And then you have to understand its boundary, because you want to say that the boundary of this thing is 0. So this is a compact one-dimensional manifold, and the boundary signed count of the boundary is 0, and then you want to say that it precisely corresponds to terms in here. So what is this boundary? So boundary of MB well, this is where we enter the realm of SFT compactness. So this is right. So maybe now I should specialize to the. Yeah, no, I think it's sort of still okay, right? So, but yeah, okay, yeah. So there's SFT compactness, and the resulting kind of SFT building of holomorphic curves will be in 2 levels. So in R cross V, which is in our example is going to use RS3, and then the bottom is in W, which is in our example of the exact filling is just RS3, and then here we have some kind of curve like this, A, 1D, and then 0-dimensional.
So you start with a unit.
Yeah. So all these zero-dimensional things bubbling. Okay, and then what do I want to say? This is exactly d of A is the count of these, and this is exactly the epsilon L of A1. So if these are P1, P2, Pm, B1, epsilon Pm. And so the contribution is exactly the boundary of this exactly consists of the curves that we would need to have when we are computing the pieces of the EL 2D. So okay.
Max, can you say in words whose boundary you're taking?
So this moduli space is a one-dimensional manifold.
What is it the moduli space of?
It's a moduli space of these disks, but with the grading of the ripcord being 1. Yeah, sorry, I kind of didn't say this.
Really? Or is it? Are you capping off all of the negative boundary components, or just one?
Sorry. I'm doing.
Usually there's no negative angle.
In the differential.
Yeah, in the different, but somehow the moduli space of which this is a boundary of. That's
Yeah, so
that's just this. We know
there is the moduli space in the interior has no outs, but as I go to the boundary, exactly it sort of extends, and then the limit will have kind of asymptotes towards the negative ends, and they will be capped off. So this whole thing together was the original. Yeah, I guess maybe I should say.
they're not defined.
Yeah. Maybe I should say B here, right? Yes, this is the end of the B, so I started with B, it bubbled, and this is the end. Sorry. Yeah. Okay.
B was someone at degree 1.
Yes.
So B was someone with a chance to have B of it not get sent to 0.
Yes.
That was the point.
Yeah, and this is the D. I mean, this is this kind of thing. You know, this is the contribution to the D, and this appears at the end of the one-dimensional moduli space. So I apply first the D to B, I get something of degree 0, and then I apply augmentation to the degree 0 thing, and I get something that's a number.
And you're convincing yourself that this number is a boundary.
I'm convincing myself that this composition number is a 0.
By convincing yourself that it's the boundary of the moduli.
Yes, that's right. It's a count of the boundary of the moduli space, and that count is 0, therefore. Yeah. Okay? All right, good. All right, so in our situation, we are now kind of here. So what about if I have a actual, a knot or a link and a conormal? So let's start with a knot. So if I have, lambda k inside U star.
At which point in this argument was it relevant that the thing was exact?
Yeah, so when I said that the boundary is this, that there are no other bubbles, this will come up right after, right? So I could have, sort of holomorphic disks with boundary on L bubbling off here,
Yeah.
and other things like this. And we're going to have to deal with this when we move to the non-exact fillings here. So it'll be much more about it. Okay, so now I have this lambda k inside U star S3, and of course I have the filling LK, the conormal. Okay, but I want to also say that there is another one, which is the. So I want to say that there is a filling with the topology of the complement of K. So I start, of course, with M tilde K inside the S3, which is the 0 section. So it is of course Lagrangian. So schematic picture, kind of in one dimension. So if I think of this point as my k, then I take the conormal, which is this is LK, and then I take MK tilde, which is the kind of the, either the whole is 3 or the complement, they kind of intersect at this k exactly. And I want to surger LK and MK to get MK tilde.
Sorry, what's written after S3, the next word?
Zero section.
Zero section.
So it's already Lagrangian, and this is Lagrangian, and then to get MK. Okay, so the
What are you calling MK tilde?
MK tilde is this thing inside the zero section. It's before the surgery.
It's just the zero section.
Well, okay, yeah. Maybe MK tilde is the S3 minus K, or depending. Maybe I should just call the zero section that. But I want to say that MK tilde and MK have the same topology, which is the complement of the. Well, whatever. It doesn't matter. I think. Okay, sorry, I was wasting time. Okay, right. So of course, schematically the surgery is just smoothing the intersection, but the description in the paper I just wanted to mention kind of briefly. So there is a way to see the surgery through the fronts. Yes.
I'm sorry, I'm starting to get lost. So, what is MK?
MK I'm going to build right now.
Okay. And MK tilde you defined as S3 minus K, right?
Yes.
Okay.
So in the surgery picture, I want to get kind of MK to be like this. So this is MK, the union of these two things, right? After I join them. Okay, so there is, this is going to be maybe rather brief. So in order to do this, what I can do is I can first perturb LK off of itself a little bit. So this is, let's say this is P coordinate, this is Q coordinate. And then I can draw the front of the resulting perturbed LK. And so this is, in this one dimension, it's an exercise in kind of keeping track of area. So, you know that when you have a thing here, you should have a cusp, and this the value of p is the derivative, so it's kind of where the cusp is pointing. So there's going to be like a cusp here pointing downwards, and then there's going to be a cusp here pointing upwards, and then you can kind of see what the thing is doing because you know that z. So this is the z direction for the front, this is q. I'm not trying to, sorry, maybe I didn't explain what I'm doing. So I'm drawing the cusp of this, the front of this Lagrangian, and then the result is that, they kind of go like this. Oh, it's up to shifting, of course. And then,
okay.
huh?
That's okay.
This is the front of LK. Of LK perturbed. Yeah, so this actually confused me for no reason because the paper says it's the front of LK, and of course the front of LK is a point. It's not a. You have to do this first, and then in higher dimensions you have to kind of spin this around. So you have now kind of Q1, Q2 maybe, and then the Z. So you take this and you rotate this, so you get some kind of spinned up front.
Abstractly, just a S1 parameterized perturbic surgery?
Yeah, I think that's right. So maybe I should, yeah. But I'm just following the paper, maybe. And so what it's doing is, it says that now, kind of you shift the zero section off of itself and then kind of merge it here by adding these kind of cusps, like this, and this connects it to the zero. So this is, I guess, the picture of the Polterovich surgery in the front projection. So if you want, you can have a little exercise and decipher what this means. But it's sort of, as far as I could tell, the picture in the, what this is doing is giving you these two, sorry, maybe I should use them. Okay. Gives you this thing, and one of them stops here, and the other one of them stops there. This is getting negative slope, so it's minus. This is positive slope, so it's plus. And then you are supposed to merge it to this black thing that you already have. This is not black. And so you just cut this off like this. And so this disappears, and you get this serger thing. Okay. Anyway, so this is the font with the fronts. So for people who, like me, are not experienced with fronts, this is an interesting thing to work out. But anyway, the whole point is it doesn't matter. You can just do Polterovich surgery and spin it around. You can do this, and then you spin it around. You spin it around the S1. So this is a picture over the normal disk of K. So I have my K, and then if I do take a little normal disk to a point, then it will look like this. And then I have to also do this in S1 family. Yeah.
What were the blue lines in the front picture?
In the front picture, what do they mean?
Yes.
They are the pieces of the zero section. So yeah.
You perturb the zero section?
Yeah, I perturb the zero section.
Why it looks like that?
I think I can just use like I can perturb it so that, you know, it ends over here, and then this is just by doing some Morse function perturbation, and then I add these things artificially. So it looks like, you know, it's coming in like this, and then I add this. So it wasn't there, you know. So I perturb, I cut off a piece and replace it by this piece.
So whatever you're doing is like the exact Polterovich surgery?
Yeah, so the point of doing it with the fronts is that then it should be clear that it's exact, I guess.
So maybe just to make sure, the ambient space on the left is T star S3, then it's J1 of S3, and then you project back to T star S3.
Well, no, not quite. Sorry, this is like the little lie. So what I'm doing, what these pictures are kind of star of the normal slice.
Yeah, slice.
And then I do all of this in the S1 family going over the
And
norm.
the surface at the end.
Yeah.
So you're defining a Lagrangian T star S3 by doing an operation in J1 of S3 projecting.
Yeah, and he's only drawing J1 or
No.
J2 or something.
Yeah, J1 of S3. Yeah. It's in. Yeah, that's right. Okay. Well, that took much longer than I hoped. Okay, so. Right, so now I have these kind of constructions, and now I want to do the transition to the conifold. So the point is that, okay, what the upshot is that we'll be able to define some kind of augmentation even when the filling is non-exact. In certain situations, it has to be augmentation admissible, right? And then, so first I want to say when do I have these non-exact fillings in the conifold, and then to describe how to modify this picture of constructing EL to get to get the augmentation from that. Okay, so let's erase this very long thing. So I actually am not going to say too much about this push-off. So LK, you know, it's basically what Abigail mentioned. So I take the so I have my knot. I have this form d theta kind of along the knot. I can multiply it by a radial function on the normal, which is so f of r function of the normal directions, and then I cut off of the neighborhood of K. And then, so I use the resulting function to make a, well, the resulting one form to do the usual symplectomorphism of T star S3. So eta sends T star S3 to itself, and P Q goes to, I'm sorry, QP goes to QP plus this one form, so one form that I'll, I don't know, alpha plus alpha. Yeah, I think that's it. Oh, sorry? Did I mess this up?
Why do you need this F?
Sorry?
Why do you need the F?
Why do I need to cut off? Well, I want to extend this to globally on the on S3.
But D of this form is probably not 0, right?
Yeah, but this is a not. So you're saying I should just forget? Yeah, sorry, I should forget this and do this on the tube.
Yeah.
And I'm not doing this globally. I'm doing this over the T star of the neighborhood. Yes.
Yeah, I think so.
Okay, that's better. Thank you. Right. Okay. So I'm doing this here, and then this is kind of defined only on this part and vertical, and then but still, it gives me so the image of LK after this is the thing LK now, perturbed, which is now inside T star S3 minus the 0 section. Okay, well, again, this is pretty trivial and took a little while, but I'm not going to say anything about the MK. So it's actually not clear that you can always do this for the MK. If it's fibered, then you can use kind of the extra kind of theta direction in the fiber to do some trick and push it off. Otherwise, maybe you have it, maybe you don't. So we'll leave it at that. But sometimes you can push off MK to T star S3 minus 0 section. Okay, so maybe you have some push-offs, and then the question is what to do about them. Well, maybe, yeah, I'm not doing so well on time, so right, so maybe, yeah, but I should probably still say this. So, if I have, so what is the mapping on the coefficients that is associated to these Lagrangian fillings? So I told you on the rep chord you're supposed to count some disk, but on the coefficients you're supposed to just look at the images of the relative H2 classes under the inclusion. So this gives a so for LK, sigma LK of P is P, right, and X goes to 0 and T goes to 0. So the topology so this is before I apologize, I kind of forgot this bit. So this is in T star S3, and T star S3 has the class right. In this filling, the S2 class is contracted, so I have to send this to 0. And in the Lagrangian LK, the longitudinal class is contracted, so I have to send this to 0. Sorry, the meridional class is contracted, so I have to send this to 0, and the longitudinal class stays as the generator. And then for MK, I do ELK of. So the other way goes. So T still goes to 0 because I still kill the. It's the same filling, and then the manifold that I'm filling with is the same, and then P goes to 0, and X goes to X. So for knots. Okay, and for links, it's a little bit more complicated because the homology. So for links, H2 of T star S3 more than K is still H1 of MK, which is generated by the excis, but the sorry.
I don't understand how this MK can ever be pushed off the 0 section. I mean, if you compute Hammond's Guy category with the 0 section, that should be the cone between Ham from fiber.
Well, this is S1 parameterized somehow.
Yeah, but nonetheless, it's a cone between Ham to conormal
Yeah.
and Ham to the 0 section. One of those has class in degree 0 and 1. One of those classes has classes in degree 0 and 3. And you're not going to kill that in the flow.
Yeah.
No.
So Floer homology doesn't have to be preserved by this. Yeah. Yeah. Okay. Sorry. Generated by. Yeah. There is some mess with the So, but you have this the situation that the longitudinal generators of H1 are no longer contracted, but instead, if I draw a ciphered surface for my components, so this is Kj, then I see that my longitudinal generator is homologous to the sum of the meridional ones, where the number of the meridional ones is given by the linking number. So I have to send up to, again, like some confusion between P's and Q's, I have to send Pj to some sum over I not equal to j, the linking number of the component Ki and Kj times the xj, xi. So, okay, this is maybe a bit too wordy, but basically, because the short version is because on the coefficients the map is given by the map on the homology, then you just see what happens to the homology and you know the result. There's no. Okay. All right. So maybe I should actually try to describe something about the non-exact moduli spaces. All right. Right. So now this is going to this section here. So the point is that we want to try to define augmentation from a non-exact filling. So let's try to define EL, augmentation for non-exact L. So we do exactly the same thing, but now we have this problem that was mentioned in answer to Vivek, that since it's not exact, it can now bound Lagrange holomorphic disks. So we can have a bubbling of the type where I have, so I'm looking still mimic the proof for exact case. And consider this moduli space of disks limiting to B. And now you can have this kind of schematic picture is like this. And then something bubbled. This is dimension 0 and this is dimension 1. This was dimension 1. Okay.
Maybe one remark.
Sorry?
Maybe a remark that all these inside the closed disk by mass of 0 and cannot be
Right. Yeah, okay. Yeah, so sure. Yeah, I should say this. So there is the computation for the so we need to consider this kind of possible disks with boundary on L, and the Maslov class of this LK perturbed is still 0, and we're in dimension equals to 3. And what else? I think that's it. There are no mark points, no nothing. So then, when you compute the expected dimension, you get some contribution like 1 minus g to dimension of manifold minus 6 or some, things like this. This is for closed case, I guess. But in any case, this kind of disappears, and the mu of the disk also disappears. So you always get 0. So whatever the formula that is the correct formula for the expected dimension of the moduli space, because of these things that we have, the result is 0.
Moduli space of disks.
Of disks, yes.
For this is n minus 3 plus mu.
Yeah.
Do you also see that it's spin or is
Yes, if I want some kind of orientation, but this is.
you do over 0?
Huh?
You do over 0.
Yes, yeah. Over C, yeah.
Over C.
Yeah.
I didn't understand your schematic picture. What is going on there?
Yeah, so I'm gonna draw a slightly better schematic picture, I hope. So maybe I won't get to like the end, but maybe I'll at least try to explain what I actually get to, right? Okay, so I have this kind of, this is happening, I have the Legendrian torus and I have LK filling it. So I have this solid torus. There's some kind of, and then here there's some kind of lambda k at infinity. This is actually three-dimensional, right? S1 cross R2. Okay, and then I have this B somewhere here at infinity. So there's some kind of rep chord, but the rep chord is kind of appears as a, the thing leaves the Legendria and goes out into T star of S3, or in this case U star of S3. So it goes out of my three-dimensional space that I'm depicting here and comes back here. So this is B. It's in extra dimensions. And then there is the boundary of this one-dimensional, of this disk in this one-dimensional moduli space. So the boundary might go around a few times and do this. So this line lies inside the solid lambda k, which is the solid torus, and that's the boundary. I'm just depicting the boundary. The disk is also in some extra space in T star S3. All right, and now there is this other thing, which is the boundary of the rigid disk, that maybe is something like this. And then this is one-dimensional moduli space, so the disks move and the boundary moves with them. And as I move this this boundary, what happens is that it's a little bit. Let's draw this here. I drew too big. Maybe. So what happens is one of these rounds actually merges with this. It sort of itself intersects, but at the point when it self intersects, it actually coincides with this green thing. And then there's and this is still punctured, going off to this B. Right. And so in the disk world, this is this configuration where things have,
Both curves there have dimension 0 right there. Can we have?
No, this is 0 and this is 1.
Main port still dimension 1.
It's still dimensional. Yeah, so it's a little funny. Like this thing can continue moving on its own. So it can continue going off to kind of, now it passed through and now it sort of linked it. How does it link? Okay, whatever. Somewhere. Green thing like this. So this green thing is stationary, and this other thing has moved. So it moved past it and continues. So this now is So if you move this, so this is kind of the picture.
But the homology class of the boundary of the disk has changed.
Yeah.
Of this remaining thing, yes,
Yeah.
but the change is exactly this thing.
Well, maybe I call it, so
Yeah.
secretly there are two modular spaces involved.
Yeah,
One is the one that you're drawing.
and then there is the one that's like this.
Let's say its boundary has homology class
Right,
e to
right.
the kx. Right?
So here it's e to the 2x
Let's say e to the 2x.
because it winds around twice.
And then there is another modular space, this split off.
Yeah, so this piece now by itself belongs to the moduli space e sub x. So this thing belongs to mu b 2x, and this thing that's split off belongs to mu b x, where x means that the boundary winds around once. Well, of course I have to again cap everything and so on, but.
And that modular space somehow is just smooth and nice. And
Yeah, smooth and nice. Yeah. So the point is that somehow, if you run this picture backwards, you can think of this moduli space that encounters this disk and either does nothing, does not interact with it, and continues, and that's the interior point of this MXB, or it attaches this guy. And then that piece goes into the kind of into this guy, MX2B, MB2X. Right. So, yeah, I don't know what else to say. So maybe I should comment that if you know this picture about, in mirror symmetry and wall crossing in the anticanonical divisor, there is a deformation of. There is a similar picture where like disks either encounter a Maslov zero disk and then either glue or not glue, and then the counts of disks change. So this is what distinguishes Chekhanov torus from Clifford torus. It's this picture. Anyway, all right. So the problem for us is precisely this, that when we get to this configuration, our MB2X ends. There is the end that doesn't correspond to these buildings that we want. So we have an end that is not accounted for.
But like, no one of your pictures is in the boundary, right? All these pictures.
Of what? Of which moduli space?
No,
So if I'm doing,
M2x.
yeah, so
it is.
in this
But
picture,
it's one dimensional, just like M2x.
No, M2X has two boundaries. So one you can imagine is the R invariant piece. With this one, the curve to the left
Yeah.
just goes off to infinity.
Yeah.
So that's one piece of the boundary. The other piece of the boundary is this MX intersecting the disk 0. So it's a specific one in MX which intersects this disk. So these are the two currently the two boundary points of this integral. And one of them we want to remove.
Yeah. So exactly like I have this kind of the X moduli space, and here there's the thing, and then I have the 2X moduli space. which sort of runs into it. And then there's another end here to be associated, so it's kind of translated. Yeah. Okay. I don't know. So what can we do about this? Okay. Maybe not so much.
And this could be multiply covered?
Yeah.
No.
What's
I mean, of course it could, but so we're assuming, if this ornament, we're assuming that this is.
we perturbed over here or something?
Yeah, everything is perturbed.
Yeah, so we have to fix.
Transversely cut out and whatever you imagine about the boundary, generic.
Yeah, so
somehow we fix some
yeah.
fancy perturbation scheme that does this.
That's right. So in particular, somehow these disks, you know, they're after some perturbation, so they should be counted with some weight, which is probably rational or something. Or, I don't know. Yeah. Oh, yeah, and I'm past the time. Yeah. So I'm not sure what I can do. Right. So what can I say? Well, okay. So what is the solution? The solution is to pick these bounding chains. So what is bounding? So bounding. So bounding chains. So for each u, follow u with boundary on L. What do I pick? I pick a sigma u, which is a chain connecting du inside L to, well, so this du inside L represents some number of of longitudinal disks. So just here, this was once for this rigid disk, but it could be more. So this green curve could be going around several times. So connecting this to the k times some sigma, where k is obtained from, so where, okay, so what do? I take du, the class, is equal to k times lambda, the longitudinal thing, and psi is a fixed circle in k, representing the corresponding plus there. So my psi is going to be this, and my bounding cochain, my bounding chain would be a two-dimensional chain connecting this boundary of u to the fixed circle psi. And I think I need to pick psi to avoid all capping paths or something. Maybe. Okay, I don't know. I think it's okay. All right, so then I use these bounding chains to modify my moduli spaces. So now I have to define, so I had my moduli space MA. Now it goes to MA sigma. And what is an element of MA sigma? Well, it's the following thing. So I start with the disk punctured with a puncture at A. And this is a once punctured holomorphic disk. Now I put some marked points. And I want to say that, so this is U. This is again a map from D2 to 3. And then I want to say that U of this punctures Xi must lie on the sigma of some ui. So it must lie on the bounding chain for some rigid disk ui that I haven't seen before. So schematically, I draw either a line, or since it's a two-dimensional bounding chain, so this.
The bounding chain is like top dimensional thing in this case?
The chain is two-dimensional. It connects the boundary to the fixed circle.
Inside LK.
Inside LK, yes. So this disk is inside T star, but the sigma is inside LK. And then right, and then here I draw the UI. UI no longer has any punctures. It's just a rigid disk with a boundary on L that I had before. So this green thing. And then of course, and then I do this at every puncture, at every marked point. And then I can allow my UIs to also have marked points and be connected to further rigid disks by similar bounding chains. So here I again have marked points.
I mean, in fact, you have to, right? I mean, it's forced.
What do you mean?
I mean, you have to.
I have to allow this.
Yeah. Or that, I mean, it tells you that the normal these potentials count in these things, not these or these things.
Yes. No, but okay. So I'm just describing a single element, and I'm saying that the element is going to be given by this rooted tree, where the starting vertex is punctured, and all the other vertices correspond to distinct rigid disks UI, and I am connecting them to each other by at each stage having the marked point on the boundary of the previous vertex mapped to the bounding chain of the next vertex. So such a structure with finitely many levels is exactly an element of mu a sigma. I'm sorry I'm not writing anything down anymore, but I think. Okay, so I can do this for A both in degree 1 or 0 and degree 1, so sort of MA sigma and MB sigma as usual. And then, so the claim, so now I define. So of course for such elements, so this is, I will call this also, I don't know, U corrected, corresponding to such a tree. So I define the class of U corrected to be just the sum of the classes of UIs and plus class of U in each one of stars. So I still want to keep track of this, with the relative homology classes that they represent. And then I define the sigma L of A, where A is of degree 0, to be again the sum, but now over all the elements in MA sigma, so U corrected in MA sigma, of the some kind of count. Sorry. So if this way I have to say, so E to the class of U. This is my thing, and then here I have to write the weight of U. So, what do I want to say? Sorry. And now I want to use this this corrected EL to, okay, so I guess I didn't tell you what the weight of U is. We're over time, yeah. Okay, I have to think of what to say to finish. Huh?
It's okay to pretend it's one.
Okay.
Check.
All right. Yeah. I think what to say. So I define it this way, and I need to understand under which circumstances. So I define it on the chord, but I haven't defined it on the coefficients of the homology. Yeah, I'm not sure what to say. So in order to actually, maybe it's best to just say, okay, let's see how, we want to say under some conditions. So let's formulate this as a question. Under what conditions in particular, for what assignment epsilon L of x, epsilon L of p, and epsilon L of q, of t, I guess, or equivalent to lambda, mu, and q. So what do I need to do? What do I need to send the x, p, and t under this corrected thing? Under what conditions, so what assignment of these does the epsilon L, which is defined on the generators this way, and then somehow defined on the coefficients. So under what assignments of the coefficients does this resulting EL give an augmentation? Okay. All right. So, and in order to answer this question, what you have to do is you have to again, you have like one tool.
Sorry, and what was the answer in the exact case to this question?
In the exact case was that, because you didn't have to correct anything and so on, this sigma, this epsilon was given just by inclusion of the homology coefficients of the Legendre relative of the top relative. So in the exact case, just I star from H2 U star S3 lambda to H2 T star S3 L. So if I just use this,
and now what's wrong with the same? I'm missing.
Yeah. So this is what's yeah.
Maybe I can say something. So somehow, in this what we just did when we have all these boundary cochains and so on. So now it is clear that you have, if you look at this moduli space, whatever you call it, M, B, sigma or something.
Right.
So its boundary.
Yeah.
So this MB sigma is counting some kind of this with insertions of other pieces. So the boundary of this moduli space is now given by two-level curves. And the two-level curves, again, are curves with these insertions possibly everywhere, right? So we know that if our DGA counts these curves, and then we have the chain map equation. And what does it mean to count these curves? Where do we count them? Well, as we saw, we count them in the relative homology class of the filling LK. So that's given by e to the x and q. So those variables remain untouched in this case. So then it's somehow, the question is, can we understand what it means to count these curves and from an algebraic point of view, and in particular in the upper part of what Max is doing, so somehow this differential now has to be changed a little bit, and we would like to have an expression for a curve. You know, this B curve goes down to 3 A's. It's some curve, and it's given by e to the x, e to the p, and q. And x and q stays. So what to do with e to the p? This is the only thing we have to explain in order to, we have to see what do we have to do algebraically to p to model the fact that we're counting all these discrete insertions. And that's kind of now what's being explained.
So, can I ask one
Sure.
more further question? What for is q equals 1 before?
Well, this inclusion of homology coefficients,
That's too long.
S2 was bounding, so the inclusion, I have this Q which represents
Because
the,
we were working in different now.
yes, I was in T star S3,
Yeah, okay.
yeah. So if I, there's no hope to have an exact Lagrangian in Y.
Yeah.
So if I had, then I could, but now I can't.
So really it's because of some of these organizations is moved past this area.
Okay, so yeah, so maybe to try to wrap up and then restate sort of what Tobias was saying. So when you look now at the boundary of this corrected moduli space, the point is that whatever you before experienced as a bubble, as a disk bubble, now can continue into this. So the bubbles, if you have something bubbling just on the top level, it is not going to be in the boundary of your moduli space. So the result is that the boundary of these corrected moduli space is given by counts of these two-level buildings again, but now here you have this kind of, again, D, and here you have some kind of EL counts. So here you have something that clearly looks like EL of A1, because you can attach to this chord that happened any kind of rigid disk tree. This will be EL of A2, and this will be EL of AN, and so on. And so the thing that you haven't accounted for is the attachment of these kind of unpunctured trees of rigid holomorphic disks, and the kind of the generating the Gromov-Witten, the corrected Gromov-Witten potential is precisely some kind of count of these rigid disks. So
Can you just explain again, what is that part of the picture with this like arm coming off and then
this.
Yeah.
So this just means that I have a one positive and a bunch of negative punctured disk in the symplectization.
Yeah.
It has some boundary marked points. Maybe actually here. I think that's not prohibited, right? It's not
Anywhere.
anywhere, right? So anywhere on its boundary there are some marked points.
Yeah.
And those marked points are mapped to some sigma of a U. So there's a rigid disk here, rigid disk here, rigid disk here, and the marked point on the boundary of the one positive, many negative puncture disk here is mapped to some point on sigma of U.
And so the point is that the boundary points which happen after converting, that's already accounted for by epsilon.
Yeah.
But now you need to do some further correction for these boundary points to happen before the break. Yeah,
What do you mean by breaking?
No, at the top level.
Yeah, that's right. So somehow, if you just bubble in the top level, then you continue by doing this somehow. Alright, so the only thing that really happens is the splitting in SFT style. Okay, so alright, so you define. Okay, maybe I should at least write down something. So you sum over all the k and r that appeared before, but this is really the sum over tau in H2 of the conifold, comma L. So here you see the Q survived because it's now in the conifold and not in the T star S3. And then I write Q to the R, E to the KX, and then here I put some kind of weighted count of corrected rigid disks. So the things that you would see here. So you can imagine the definition is basically the same as the one with the puncture, except like no vertex now has a puncture. That's it. Okay, so this is schematic thing, and then so you see that this is the thing that will need to account to the fact that you are attaching these things. And so the only thing to notice is when you're weighing these things, there is some kind of class of the boundary of this U here. It wraps around, and you want to see how many times the boundary of the disk that you're counting here intersects the sigma U. Because that will tell you how many places you can attach this whole bubble tree. And so the point is that this thing is some kind of L times X, because it's in the filled in thing, so P does not appear. And the boundary of this will have some kind of like M times P plus KX plus something. What did I say? RT. This is the class of the boundary of the top. And this sigma U that I have here will have an LX and maybe some plus something Q. Yeah, plus something Q. Class sigma. All right. So the sigma, how many times can I actually attach it to the boundary of the top thing? Well, the pairing is that I have to how many times do these curves intersect, and this gives me a factor m as before that is already included in the boundary thing, but the L comes down and is an extra factor. So this L coming from the number of times that the sigma U wraps around the longitude appears extra. So I'm sorry, yeah, this is very hand wavy. So every term, so I need to to ensure. So in other words, to answer the question, so answer to the question. As Tobias was saying, X goes to X, T goes to T, but I need to send P to what? Well, to something which counts, again, all these things, but where every term that I have here, whenever I have this K, I have to kind of add an extra factor of K. And that is precisely, so if I resum with like whatever, the same as before, but now I sum K, e to the Kx, QR, I see that this is dW, dx. So this derivative, this mysterious derivative, is nothing else than just, before you were, you were summing with whatever weight coefficients, and now you add an extra k to your weight, and algebraically that's derivative.
And so the statement is that this is what you need to do to the boundary of this moduli space has a property that that's what I have to do.
Yeah. So if epsilon L of P is equal to this, and epsilon of X is X, and epsilon of T is T, and the chords are sent as we described, then EL composed with D is equal to 0. Okay, and this is how you get your augmentation. And again, you have these coefficients now. You still preserve the X and the T coefficients, And so then you can send them to whatever you want, and so you have a parameter space of what to do, and you parameterize actually a whole branch of the augmentation variety, because you still have the freedom to move these things. Okay. All right. I don't know. I guess it's way over time, so I won't say anything else.
Any questions for Max?
So I think I would wait and postpone the questions to a discussion session. Maybe in 15 minutes. We should pick up again at 5:30 for people who are interested in being a follow-up discussion.
Yeah, so I'm going to try to summarize what everybody has done today, and then I think
Yeah, I think
maybe
Tobias
Tobias
will
might
say
have
a
had
few
some
words too.
things to say. But yeah, it's optional, and you can leave.